Hello everybody. In this video series, we're going to go through joint probability. This is example 1. Before we start solving example 1, let's go and review good to know chart. It is must to know the definition of joint probability. Joint probability, in our case y is less than or equal to x, is equal to probability that both x and y are in the region. That is double integral of the region, fx of s, fy of t, dr. We're going to decide whether ds dt or dt ds order here. It is must to know density functions of the given random variables to start the problem. In our case, we were given both exponential random variables. We know that in general, exponential random variables are defined as lambda e to the negative lambda t if t is greater than 0 and 0 elsewhere. So in our case, fx of s with parameter a will be a e to the negative as, like lambda e to the negative lambda t if s is greater than 0 and 0 if s is less than 0. And the graph of our density function will be 0 up to 0, and greater than 0 will be some decaying function with the top point a. So our y exponential random variable will have the same density function. Fy of t with parameter b will have b e to the negative bt if t is greater than 0 and 0 if t is less than 0. And the graph of the density function will be exactly same. 0 up to 0 and some decaying function if t is greater than 0. And the top point of the graph will be b. Now let's review the steps to start the solution. We're going to start with the definition of joint probability. That is probability that in our case y is less than or equal to x is that probability both x and y are in the region. That is the double integral of the region, fx of s, fy of t, dr. Now we will decide whether ds dt or dt ds order and simultaneously the limits of integration. Let's set up our double integral. Write fx of s, fy of t, and we will decide now. Let's see the relationship between x and y. And let's associate them with st, and let's graph it on the st plane. Y is less than or equal to x. Let's associate it with s is less than or equal to t. We know that this inequality is this curve, and we need to pick up the test point, whether above the line or below the line will be our region. Let's pick up some test point here. The coordinate of this point is 0, 1. And let's see whether this is correct for s is less than or equal to t. S coordinate is 0, less than or equal to t coordinate is 1. So this is true for this inequality. So the region above the line is our region to integrate. Now we're going to decide the limits of integration and ds dt order. This is easier to integrate on the t direction. Our lower boundary, lower curve is s, t equals to s. So starting from s to infinity on the upper boundary, and from left to right it is negative infinity to positive infinity. This line is going to infinity, coming from negative infinity. So our limits of integration will be naturally dt ds. Since we are integrating dt first, we can use it at we can use it as our inner integral. So we can take out fx, integral from negative infinity to positive infinity, fx of s, integral from s to infinity, fy of t, dt ds. Now we know that this is our inner integral. Let's call it I of s. So our new integral will be integral from negative infinity to positive infinity, fx of s. Instead of fy of t dt, we can now use I of s and ds. Now we're going to decide what I of s is as our next step. So we can do side work here. I of s, here if s is less than 0, which will be the entire region of the density function. So it will be 1. 1 if s is less than 0. Then it will consist of s to infinity, everything, if s is less than 0. If s is greater than 0, then our density function will be integral from s to infinity, as defined here, b e to the negative bt dt. So the integration of this area will be our density function if s is greater than 0. Now we can integrate this. So integral from s to infinity, b e to the negative bt dt. Now we know how to integrate this. Antiderivative of e function will be negative 1 over b times b e to the negative bt, which will cancel out and make negative e to the negative bt from s to infinity. So if we plug in upper boundary, e to the negative infinity goes to 0, minus, if we plug in s lower limit boundary, we're going to get negative e to the negative bs. So we obtain negative times negative is positive, e to the bs, negative bs. So this is our inner integral. Now we can use, instead of I of s, e to the negative bs. So our new integral from negative infinity to positive infinity, fx of s, e to the negative bs ds. Now we are going to decide what fx of s will be. We know that our density function for x is a e to the negative as if s is greater than 0, and 0 if s is less than 0. So our lower boundary supported from 0 to infinity for exponential random variable. So our density function that we're going to use will be a e to the negative as, because anything less than 0 has no contribution to the density function. So instead of negative infinity to positive infinity, we can change the limits of integration from 0 to infinity and use the density function a e to the negative as for fx of s, and we calculated I of s already, which is e to the negative bs ds. Now we can perform this integral. We can take a out, integral from 0 to infinity, and we can merge the powers of e, which will be negative s to a plus b ds. Now we know antiderivative of e function will be 1 over negative 1 over a plus b times everything here, e to the negative s times a plus b. And we can take out negative 1 over a plus b as well, so it's going to be negative a over a plus b times e to the negative s times a plus b from 0 to infinity. If we plug in upper boundary infinity, it will be e to the negative infinity, which will go to 0, minus the lower boundary. If we plug in 0, it will be e to the 0, which will be 1. And if we distribute this, negative times negative this fraction times negative 1 will be positive, a over a plus b. So we can conclude that probability that y is less than or equal to x is equal to a over a plus b. Here a was the parameter of random variable x and b was the parameter of random variable y.